Hello everyone, welcome to Guide My Career. This is Siva from Department of Meteorology and Oceanography, Andhra University. In our first video of Basic Statistics for All, Part 1, we have covered all few basic and fundamental statistical parameters such as a mean or average, bias or error, covariance, standard deviation, Rmse, scatter index, and correlation. Right? We have covered all the 7 basic fundamental statistical parameters in detailed manner in Part 1. Right? So in this video, we are going to calculate those parameters by using a sample data, right? So here, the column which is highlighted in blue color, light blue color, that is observational data, and another column which is highlighted in the gray color, that is the forecasted data, right? So you can imagine, okay, for example, you can imagine this data is wave height, which is derived from the wave height in meters, which is derived from the wave rider buoy, right? And this is the forecasted data, which is also in meters and also derived from the spectrum model, wave numerical model, right? So you have two data sets. One is observational data and another one is the forecasted data. So when you have a data set like this, how to compute all these 7 basic parameters, right? This is what we have to do. This is our task. So now the next column, that is named like a bias or error, that is F minus O. Here the F stands for the forecast and O stands for the observation. So this column indicates actually the difference between the both observation and forecast. That is, if I place the cursor here, what you can see, that is a C4 minus B4. That is, C4 is the forecast value, that is 2.2, minus B4 is the observation value, that is the 2.3. So the difference is minus 0.1. So this column indicates the difference between the forecast and observation. And the next column, that is F minus O squared, that is just nothing but the square of the F minus O, right? That is a square of the column D. So we can call it as like squared difference between the forecast and observation, right? And then the next column indicates that this is the difference between the observation data and mean of the observation. That is, if I place the cursor in this cell, what is it showing? See, B4, that is observation value, that is 2.3, minus mean of the observation. Of course, we can calculate the mean by adding of all these points in this observation data and divide by the number of data, that is n equal to 20, right? So you can see here, like this is the summation of all this data, that is 54.5, and divide it by 20, so that you will get the average, that is a 2.75. So that is a 0, sorry, O bar. So the column here, it is nothing but the difference between the observed data and mean of the observation, right? That is O minus O bar. Similarly, in case of forecast, F minus F bar is nothing but the forecasted data, difference between the forecasted data and mean of the forecast. That is represented F minus F bar. And next two terms are nothing but the square root of the O minus O bar and F minus F bar. That is nothing but the square difference between the observation and the mean of observation, that is termed as O minus O bar squared. You can see that is a square of the F column, and square difference between the forecast and mean of the forecast, that is represented as F minus F bar squared. It is nothing but the square of the G column, right? See, if I place a cursor in this cell, what it is showing? Z4 into Z4, that is the square of the Z column. Okay, and the final column, that is 0 O minus O bar into F minus F bar, that is nothing but the product of the two differences, such as the difference between the observation and the mean of the observation, and the difference between the forecast and mean of the forecast, right? So product of these two columns, that is column F, column F and column G. The product of the column F and G, such as O minus O bar into F minus F bar, this column, say product of this F and G, nothing but the O minus O bar into F minus F bar, right? So these are all the columns which we have elaborated in such a manner to simplify our calculations and substitute all the terms, corresponding terms in the formulas of those 7 parameters, right? And also we'll have a look on end of that columns, what are all these. So of course we know n is nothing but the number of values presented in that data, that is nothing but 20 data points are there, so n will be 20. And sigma o, that is nothing but the summation of the all observations. Similarly sigma f represents the summation of all forecasted values. And when you divide that sigma o by n, you can automatically get the mean of the observation. Similarly, when you divide sigma f, that is summation of all the forecasted data, by n, then you will get the f bar, that is the mean of the forecast. Similarly, sigma f minus o, that is nothing but the summation of the differences between forecast and observation, f minus o, right? So when you divide it by again n, that is 20, then you will get the mean of the f minus o, that is the f minus o bar. Like this you will get the summations and corresponding averages for observation and forecast, and mean of the observation and forecast, sorry, difference between the observation and forecast, right? And also you will get the square difference between the observation and forecast summation, as well as the corresponding mean, right? So now you will also get the summation for the these 3 columns, such as square difference between the observation and observation mean, that is the summation of the O minus O bar squared. And similarly summation of the square difference between the forecast and mean of the forecast, that is termed as some sigma f minus f bar squared. And similarly the final term, the summation of the two differences, the summation of the products of the two differences, such as the difference between the observation and mean of the observation, and the difference between the product forecast and mean of the forecast, that is a sigma o minus o bar into f minus f bar, right? So we have computed all these we have created all these columns and computed all these summation terms and mean terms. Now we'll good to go to compute each one of our parameters, like 7 basic standard statistical parameters, such as mean, bias, variance, standard deviation, Rmse, scattered index, correlation, right? So as we already know, know well that, and it's very easy to compute that mean. So it's nothing but the summation of the all observations and number of the observations in number of the data points in that observation. That is summation is 54.5 divided by n, that is 20. So if I place the cursor in this cell, what it is showing, B24 by 20. What is the B24? That is nothing but the summation of all these data points, that is 54.5 divided by n, that is n equal to 20. This is what I did in this place. See, when I place the cursor in the O bar, that is the mean of the observation, it is showing B24 by 20. That is the summation of all observations divided by 20. And similarly, you can get the mean for the forecast data, that is 2, that is this divided by 20, right? That is nothing but C24, that is sigma f equal to 56.8 divided by 20, that is f bar equal to 2.84. Similarly, the mean or average error, this is the summation of the differences between the observation forecast and observation, that is 2.3. So when I divide this 2.3 by 20, so I can get the mean or average bias or error, right? And coming to the variance, of course we know we have a formula for the variance, that is a summation of the square difference between the observation and mean of the observation divided by the n, right? So if you see very clearly, we have computed the numerator of the variance. Is this the term summation of the difference between the observation and summation of the square difference between the observation and mean of the observation? Is the term same as the numerator of the variance? Yes. So we have computed this term, that is the 14.538, and if I divide this term by simply the n, that is the 20, so that I can calculate the variance for the observational data, right? That is what I did here. You see, H24. This, what is the place of this cell? That is the H24. So I divided the H24, that is sigma O minus O bar square, that is a 14.538 divided by N, that is a 20. This is what I did, H24 by H24 by 20, so that I can get the variance for observation. Similarly, I also get variance for the forecast, that is I24 by 20. I24 is nothing but sigma F minus F bar squared, that is 15.188 by 20, so that I can get the variance for the forecasted data. In such a way, I can compute. We can compute the variance for both observation as well as the forecasted data. And coming to the standard deviation, we also know that standard deviation is simply the square root of the variance. So whenever you have a variance for that cell, if you apply the square root, so that you will get the standard deviation. That means, see, if I place the standard deviation for the observation data, what I have to do? Simply square root of the, what I have done here is the square root of the L9. What is the L9? L9 is nothing but the variance of the observation data, variance for the observation data, right? So if I apply the square root for that variance, so that I will get the standard deviation for that observational data, right? In the same fashion, I also computed that standard deviation for the forecast data, that is nothing but the square root of L10. So here the L10 is nothing but the variance for the forecasted data, right? So if I apply square root for the L10, so that I will get standard deviation for the forecasted data. So simply we can, if you get the variance, if you apply the square root for the variance, you can get standard deviation, corresponding standard deviations, right? So once if you also calculate the standard deviation, you can good to go to calculate the Rmse. So it's nothing but the, again somewhat related to the standard deviation. So as per the definition of the root mean square error, is nothing but the standard deviation of the residuals. Here the residuals are nothing but fi minus y squared. So if you see the formula of the standard deviation, in place of the oi minus o bar squared, there this term, oi minus o bar squared term, will be replaced with fi minus y squared, right? So we have the whole numerator term here. If you see this sigma f minus o squared, right? This is what the numerator of this Rmse formula. Am I right? Sigma f minus o squared, that is 0.51, and we have also n denominator n we have, that is the whole this part is whole, this whole part belongs to this numerator and denominator, right? Sigma f minus o squared divided by n. And I computed this numerator as well as denominator. So if I apply square root for this part, so for 0.0255, so that I will get the RMSE, right? So root mean square error, that is, see what I did. So this is the numerator and this is the numerator and denominator. This term indicates the numerator and denominator of the RMSE. So what else left? Only square root. So if I apply the square root for this term, that is a 0.0255, that is a summation of f minus o squared divided by n, so that I will get the RMSE. So this is what I did, SQRT of E26. This is E26 only. So when I apply SQRT of the E26, so that it means I substitute this formula, right? So that's how I can compute the RMSE. And coming to the scattered index, if you once compute this RMSE, so that you can simply calculate the scattered index by just dividing the RMSE by mean of the observation, that is O bar 2.725. So this is what I did. So when I place the cursor in place of this scattered index value, what it is showing? L15 divided by B26. What is L15? L15 is nothing but RMSE. What is B26? L15 is RMSE divided by, what is B26? B26 is mean of the observation, that is B26. So scattered index is nothing but the RMSE divided by the mean of observation, that is L15 by B26. So that I got the scattered index value. So if I want to get the scatter index in terms of percentage, I can simply multiply the scatter index with 100. That is, I have to multiply L17, that is the scatter index value, into 100, so that I'll get the scatter index in terms of percentage, that is 5.86. If my scatter index is a value, if my scatter value of the scatter index is 0.05, if I convert that into percentage, so that I'll get the scatter index as 5.86 percentage, right? In the same manner, I can also compute the next parameter, that is correlation. So if you see the formula of correlation, so any one of these three formulas we can use, but in this video I have used this formula to compute the correlation manually. So if you see carefully, the numerator of the correlation formula is nothing but sigma I equal to 1 to n oi minus o bar and fy minus f bar. The whole numerator is this. Is this term somewhat look like uh, is this term same as the numerator of this formula? Yes, this is a sigma O minus O bar into F minus F bar, right? Sigma O minus O bar into F minus F bar. So, can we take it as the numerator of the formula? That is a 14.74. So, we have the numerator, and these two, we have these two terms, right? So, we have sigma OI minus O bar squared, sigma Fi minus O F bar squared. That is, we have sigma O minus O bar squared and sigma F minus F bar squared. So when you have a numerator and you have the two terms in the denominator, so what you have to do, you have to multiply these two terms and apply the square root. So then it will be act as a denominator in this formula, right? So this is what I did. You see, when I place the cursor in the value of correlation, what did I do? What did I do? You see, J24. What is J24? This is numerator of this formula, right? Divided by square root of this term and this term. So square root of, what is this term? H24. What is H24? Sigma O minus O bar squared. O minus O bar squared into I24. What is I24? Sigma F minus F bar squared. This is I24, right? So J24 represents the sigma O minus O bar into F minus F bar, divided by square root of H24 represents the sigma O minus O bar squared into I24 represents the sigma F minus F bar squared. This is what the definition for the correlation, right? So if I click on enter, so that I will get the value of the correlation, that is 0.99. That is, which is very near to the positive correlation. That is, since it's near to the 1. So, but if I want to get the correlation in terms of percentage, just like how did we do in case of scatter index, simply we have to multiply that correlation into 100, right? That is what I did. L20, that is the value of, and this is the place of the cell where we have stored that correlation value. So if I multiply that value into 100, so that I'll get the 90. If I got the correlation 0.99, so when I multiplied it with 100, so that I'll get the 99.19. So there is a strong correlation between these two data sets, that is 99.19 a percentage of the strong 19% of the correlation existed between these two observation and forecasted data, right? So this is how we have to represent the correlation data in terms of percentage. But in case of Excel, you can also compute the correlation parameter by default. By default in Excel, there are some inbuilt functions to compute all these parameters like mean, bias, error, variance, standard deviation, correlation, Rmse and all, right? So, but just make you to understand, like whoever not familiar with all these terms and the first time those are seeing and computing all these terms, so it's quite easy to see how do we do with the all data sheet and exercise with all these columns and all, and substitute all the terms in a corresponding formulas and all. But if you are familiar with all these terminologies and all these parameters, simply good to go ahead with the default functions existed in the Excel sheet, such as correlation and average, sum, mean, variance, like that, right? So this is all about how to calculate the all basic 7 statistical parameters when you have a data like this, when you have a data like observation and forecasted data with 2 data sheets, right? Hope you all understand. So if you want to understand all these terms, you can just try with your data. Thank you.